Good evening, students. Start with the class. Today's class will start with the topic that is conservation of angular momentum. We had seen already this topic is done. What is angular momentum? Angular momentum is indicated by the letter V, this L. Where L is I into omega. I is moment of inertia. And this is your angular velocity. Because in this, what is that? Linear. This is what for rotational what we are doing. In translational, momentum is always indicated by P. P is mass into velocity. So in this, I told you all, instead of mass, we use mr square. Inertia is the equivalent of mass in rotational. So if in this is m, this will be I. Like how this is s, this is theta, v, this is omega. So mass is always equivalent to inertia, and v is always equivalent to omega. So we use the letter. If here it is P equals to mv, then here it is L equals to I omega. And then we know that this also we have to know, that is relation between torque and angular moment. Torque is always equals to dl upon dt. This is the relation. Now we'll come to the principle of, if anybody asks you what is the principle of conservation of angular momentum, so this is the principle. It states that if there is no external force or if there is no external torque, acting on a rotating body, then the angular momentum of a body remains constant. Then angular momentum of a body remains constant. So what it is basically trying to say is, imagine anything that is rotating. Okay, now this is the body that is rotating. If there is no external force acting on it, imagine a fan itself, if it is rotating, as long as there is no external torque, means no extra force other than the normal which is rotating, nothing is, that means the angular momentum of a body, that is what L I omega. So it basically says that if torque is zero, external torque, you can say, this is for your own, in your own words, huh? This is as per the definition, this is for your understanding. If external torque is zero, means there is no external force acting on it, then L is equals to I omega, that is the angular momentum, which is inertia into your velocity, angular velocity is constant. Constant means what? Before initial also, after certain motion, initial also, if you check the angular momentum and the final momentum, it should always remain the same. Okay, if there is no other external force acting, the angular momentum always remains constant. That is initial momentum equals to final momentum. Why do we get so? Because just now we saw that if torque is zero, what was the relation? This was dl upon dt. So this is also equals to zero. Taking when is a derivative of a this, we know that derivative of a constant is always equals to zero. So we assume that L is constant. This is the formula. Torque is what? Derivative of angular momentum with respect to time. Now we know that torque is zero, means external and no other external force is acting on it. So if torque is zero, that means dl upon dt is also zero. When you will get dl upon dt as zero? Only when that L is constant. Because if it changes, it's a variable, then definitely derivative of a variable is never zero. Derivative of this constant, so this has to be a constant, that's why you must be getting this as zero. So therefore L is constant. So initial momentum is equals to final momentum. So whatever is L initial will be equals to L final. So I omega, initial also you can put, so no matter what, if this one increases, the other one has to decrease so as to maintain the constant thing. What is this? It means if, what this basically means is, if moment of inertia increases, then the velocity has to decrease. Increases, angular velocity decreases. If moment of inertia decreases, angular velocity increases. Why? It has to remain constant. Basically, suppose if you want to keep this constant 20, okay, this angular momentum should be at 20. Now if this is 5, then this will be 4. Okay, 5 into 4 will give me 20. But suddenly suppose moment of inertia decreases to 2. Okay, so 2 into this 5 will not give me 20, it will give me 10, but I want to keep it constant, I want to keep it fixed at 20. So if this becomes 2 means I'll have to increase, automatically this should increase angular velocity to 10. So 2 into 10 should give me 20, that way. Okay, so in order to maintain a constant number, if one increases, the other one should decrease. So this is the logic. Now based on this, there are some applications which you need to know. Okay, real life applications which makes use of this angular momentum conservation. I'll just share a slide. The first one is a planetary motion. Okay, but just before sharing, I'll just explain what is this moment of inertia also, what happens, how is it related with the distance. So this is understood. If one increases, if this one is increasing, this one will decrease. Okay, this. How, when is this possible to increase? Moment of inertia increases. Okay, if the distance increases. Why? Because it is mr square. R is what? Mr square. So if r increases, automatically if you are increasing this number 2 square, if it is, then this is this. If you make it 4 square, obviously I will also increase. Moment of inertia. If distance increases, moment of inertia increase. And now I'll show you the planetary system. The first application is the planetary motion. I'll give notes on that. One second. Let's share the slide first. Next day. Now look at this. If you notice, the universe, that is the path of any planet, is elliptical. It's not exactly circular around the sun. This is the first thing what you should know. Okay, it is more of elliptical in nature, like this. So this is a fixed path. Okay. Now the Earth is moving. Now who is our main reference? The sun. With respect to sun, we are talking about now. Now towards January, the Earth is closest to the sun, and by the time it reaches like July, August, and all, it is away. Again, when it comes till November, December, it will come back close to the sun. So this must have understood as per the distance. So we just draw it again. So we'll see what happens to the velocity and the moment of inertia. These are the applications. The first one is the planetary motion. The Earth is rotating. So this is around January we wrote. Maybe this side it is later, the other months. Okay, we're not bothered. Maybe July, August, and all. No one will ask you as per the month. Okay. what basically we have to tell is, as Earth comes closer, yes, this is R, and from this R is, this is more and this is less. Okay, so R is what? Distance of Earth from Sun. So when it is less, distance is less, what will happen? Moment of inertia will be less, correct? Because you know that I is what? Mr square. So if this is less, means this will also be less, always. If distance reduces, moment of inertia reduces. Now what will happen to the velocity? As per law of conservation of momentum, what has happened? Moment of, okay, when R is reduced, moment of inertia got reduced. What was the formula? So what has happened? If moment of inertia is reduced over here, because distance has reduced, what will happen? Velocity will increase. If this reduces, I told you, this other one increases. Here we cannot say if this reduces, this one increases. Mass is a constant. Suddenly Earth, mass of the Earth will not increase. Okay, so if this reduces, this will automatically reduce because it is on the opposite side of the equation. But if you see this is on the same side of the equation. So if this reduces, this one increases. Yeah, both the side it will reduce. So if moment of inertia reduces, velocity, angular velocity will increase to counter this. Therefore, Earth spins faster. So if the Earth is spinning faster means your, okay, the velocity will increase. So there will be less amount of sun available. So it will spin faster means when it is close to the sun, there will be less. So nights are usually lengthier over there. Okay, so only thing what you need to know is if the moment of inertia, I did not write, decreases, reduces, angular velocity of the Earth increase. This is the first application. Same what happens at this point when sun, when Earth is away from the sun. Once again, what happens? Distance increases, the moment of inertia increases. If this increases means velocity decreases. First application. Then the second one, Whenever a diver, okay, whenever he wants to swim, if he dives from a height, you must have seen, he will, the moment he jumps, no, he tries to keep his arms very close. Okay, a diver will always try to keep his arms closest to the feet. Now, when he is exactly standing, what has happened? That length, the distance from the moment of inertia means that L will increase. Okay, so the moment he tries to bring it closer, your distance is reduced. Moment distance reduces means what happens? Moment of inertia is also reducing. If moment of inertia is reducing, so his velocity will increase, angular velocity. So he is able to turn and spin faster. Okay, within a short time, how many, like however he wants to spin himself, that helps him to spin. So for a diver, so it's the same concept. The moment angle this reduces, so I read out. So when the distance reduces, what is going to happen? The moment of inertia will also reduce, and then speed will increase. So he is able to spin faster in the mid-air when he is in the space. So just before hitting the water, what he'll do again? He will again stretch out his arms. Why? He don't want to fall with a very great speed in the water. When he's about to reach, he will just stretch his arms. So what will happen? Again, his body distance will increase. So moment of inertia will also increase, but speed will reduce. Second one is diver jumps. A diver jumping from a springboard exhibits somersaults in air before touching the water surface. How is it able to do so? So how does he do this somersaults? Quick spinning. After leaving springboard, after jumping from springboard, diver curls his body by pulling arms and legs together. So what is going to happen? Therefore, distance reduces. Therefore, moment of inertia reduces. And what if moment of inertia reduces means? Therefore, angular velocity increases. So velocity of spinning increases. Therefore, the diver can spin faster in mid-air. Then just before hitting the water, diver stretches, means open up his legs and again. What will happen? Distance increases, Therefore, moment of inertia increases and velocity reduces. This increases, definitely this will increase. I told you this is same, and this is always opposite of this. Okay, this is about the diver application. Next application. Okay, when a person is rotating on a turntable, when you must have seen these dancers and all, and suppose if they want to spin on a table and all, they can always change the speed. Okay, so if they want to reduce their speed, no, what they will do, they will open the arms, they will stretch the arms. The moment you stretch the arms, okay, so you are trying to increase the distance. So what is going to happen, the distance will increase, the moment of inertia will definitely increase. So if moment of inertia is increasing, the speed, okay, of the rotating of his rotation will decrease. So in case he wants to slow down, no, so he will always open the arms. And suppose if he wants to spin faster, he will bring those weights together, like close to the body. So the what happens, that distance from the center of mass will reduce. Okay, and then moment of inertia will also reduce. If that is reducing, means angular velocity is increasing, so he can spin faster. This is the third application. Okay, so whenever he stretches the arms, so when arms are stretched, distance increases, moment of inertia also increases, velocity decreases. So therefore, turntable slows down. Second, when weights are taken together and so brought together, when he brings them closer, brought closer, you can say, distance reduces, the moment of inertia also reduces, therefore velocity increases. Turntable can spin faster. They can spin the turntable faster by the movement. So whenever you want to stop, suppose, you will always stretch the arm. And the fourth one is the ballet dancer. Wait 1 second. I'm not able to share that something with you. I'll just take a screenshot and then share. Okay. So any ballet dancer, if they want to increase or decrease their speed, so this is how they do. Whenever they want to reduce their speed, they will always stretch the arms. And if they want to spin fast, you must have seen, they will always hold their arms and try to keep the body as close as possible. Okay, so what happens in the first case when they open the arms, the distance is increasing, same logic. Okay, so whenever something like this is come, apply the same logic. Just think, distance will increase, moment of inertia increases. Some both are increasing, the third thing will always reduce. Velocity will reduce. The other one, there when their body is closer, the moment of inertia will reduce, so angular velocity will increase. The fourth one, the fourth one is actually there in these notes. Must have given you all these notes. Even this is there. Okay, you can directly check this. I will just write and keep ballet dance and folds hands. Distance decreases, moment of inertia decreases, velocity increases. Therefore, spins faster. When stretches the arm, even if you don't mention this distance, it's fine. This is for your understanding. Okay, in the notes, you will not they will not mention about the distance. What they talk about is only this and this. I want to tell why this is happening because of the distance. But this is actually enough to explain. Okay, slows down. This helps in slowing down. So if they want to come to rest, they will always open the arms. They try to stretch the body maximum possible. So these are the applications. So even if you come across another application, apply the same logic. You can see what is kinematics. It is nothing but it deals with study of motion of objects. All these velocities, accelerations, without reference to its causes. We don't want what causes the motion, just want the velocity and all of the motion. Under linear, we had studied that which all are the kinematics one, that is acceleration, okay, displacement and velocity. These are the three things which we had seen in linear. This only difference here is we'll see it in terms of rotational now. We don't want what causes the motion. Okay, we don't want what causes the acceleration. We don't want what made the object move. When the object is in motion, what all matters, that is the thing. So for linear, it is normal displacement. It is same for both linear and this also, only the way we write will be different. Velocity and acceleration. The only word, this is linear, and here it will be called as angular. Angular displacement, angular velocity, angular acceleration. So this is S, this is V, this is A, this is theta, this is. So these are your kinematics. And we had three kinematics equation here. Which were the three kinetics? This is for translational or linear means the same. Huh? Kinematic equations you write. The three equations. First one was always V equals to U plus AT. Second was S equals to U UT plus half AT square. Then or V square minus U square is equals to 2A. Same thing. So this is for translation. Now only thing we have to find for rotation. So rotational it will be instead of V, which letter we use? Omega. So we cannot use V and U now here. Means here initial and this we use. For this one we'll use V naught as your initial. This will use as the final. Instead of U we'll use this dash omega naught. And instead now this will be alpha t. Instead of acceleration, this will be alpha. This will be theta. So these are the kinematic equations in both the cases. This is what is dynamics. which causes, okay, previous one was what? The object was in motion. We were not bothered what causes the motion. Here it will be what? What is causing the motion? That is dynamics. So you know the only thing that can cause is external force. So in linear we used to use the word force. Here we'll have to use the word torque, or basically work done by torque. Okay, now I'll give you the entire analogy, all the relation between translational and rotational motion. Quickly write it. Like it's like a table. You can just remember. Will be easier for your reference rather than going through the entire chapter looking up here and there. Analogy between translational, or also called as linear, and rotational motion. You'll already have, no need to write. You can just see, right? Just note it down and keep. So these are all your quantities which I'm giving. So one is for linear, the other one is for rotational. First one is, it's all over again, just a revision, right? This is displacement is given by S, velocity is given by V, third acceleration is given by A, force is given by F, mass is given as M. These are your basic quantities. This side, this is called as angular displacement, given as theta. Second one, angular velocity, called as omega. Third one, angular acceleration, alpha. This is called as torque instead of force, that is tau. Instead of mass, it is called as moment of inertia, I, or mr square. So these are the quantities. Next, all the equations. Equations or expression, or formulae. This is for linear. For translational, it is a. This is for rotational. First one, velocity is change in distance upon time, angular velocity, W is d theta upon d. Here it is, acceleration is change in velocity upon time. Here angular acceleration, alpha is change in velocity upon time. Third one, your force is what? Mass into acceleration, or force is change in dp upon dt, which is same as your torque. Tau is, instead of mass it is what? I. Instead of a it is alpha. Or perpendicular, or tau is what? dl upon dt. L is nothing but I into omega. Fourth one, work done is force into displacement. Your work done is force means displacement means theta. You just have to change the notation. Force means tau, S means theta here. Fifth one, kinetic energy. Here it is half mv square. Kinetic energy over here is half, m means I in rotational, and v means this is linear momentum. This is called angular momentum here. Instead of m it is I, instead of v it is next is power. This you use a different small p, okay? Because this power and this should not mix up. This also mix small. Power L is capital. Force into velocity. Your power instead of force it will be tau into m. If you know this, automatically can change this. Okay, these are the things. Next is dimension comparisons if you want. Anyways, mass is 0. It is LT minus 1. M0 LT. Yeah. This is for linear and this is for this one, rotational. For angular velocity, there is no length involved. Because angle is always indicated in terms of time, hours, minutes. Second one, acceleration. Angular acceleration. Mass is only m. Moment of inertia. Moment of inertia, you know that it is mr square. So this is your what? Mass, and this is your length. So m will be 1, length will be 2. Or torque. Torque will have this I means extra always length square. That's why this will be m l square t minus, because torque is always I. There's I in there. I into alpha. I means what? Mr square. Square here. Kinetic energy. The kinetic energy is but it is the same there. Next is momentum. Your angular momentum is ml2 t raised to minus. And power is same. Power is same for both the m l2 t raised to minus 3. Power you already know from linear. Even if I don't give, it will be there in the list. Okay, power, same thing for both. Power will not change. So these are the notations. And the last topic, that is the rolling motion. Okay, what is the difference between a rolling motion and a rotational motion? I can say the fan is rotating, but I can't say the fan is rolling. Okay, when I kick a football, I can say the football is rolling. Why? Because there are two types of motion involved there. It is going in front also, at the same time it is rotating among with itself. Okay, a fan is fixed there only and just spinning, but it is not moving in front, forward or backward. So that is only purely rotational. Now this rolling motion is nothing but a combination of rotation with translation. It's like how there's a, this is also spinning as well as it is going in the front also. If you consider any disc, now this is rolling, suppose at every point, now suppose it is coming to a halt. Now this point, if you compare, when this movement is happening, the moment this point reaches here, just imagine this point in contact with the surface will always be at rest. Compared to this, so this part of the body is suppose moving, the moment this comes here, for a small short fraction of a time, it looks like as if this point is on the rest. Because what is trying to move, the upper part is trying to go in front. Okay, the upper body part, it is, this fellow is there only. This fellow will not go behind. Okay, this point is not going to reach her, but this point after some time will try to go here. So what is happening, this is trying to move forward, but comparatively you can assume at a fraction of a second this is like stopped here, and this body, this upper part is moving in front. So for any, at any instant of time, the bottom of the disc which is in contact with the surface is at rest on the surface. Now provided this is not slipping. Okay, what is slipping now? Imagine this ball. Okay, this is at this point. Once it rotates, this will come up. But imagine this ball was slipping. Means what? You are trying to push this. You are holding, putting some force and just drag this on the floor. Okay, like imagine you are just trying to push a box. So same way, without rotation, you are trying to keep it here only the point. You just mark with a red color here. That red color should not go up. So you are not making it rotate. So imagine if you are just trying to slip it. So this red point will just everywhere, when you are just pushing it, this red point will remain here only. But if it is purely rotating, then this, after some time, this red point would have gone up. Okay, so slipping is what? When the point keeps moving. If this point keeps moving this side along the surface. Okay, it remains there only. Or maybe it is also called as sliding. The ball is sliding. So you see what happens to the velocity. We'll consider there's one disk which is rolling on the floor, some velocity, maybe angular velocity is omega, and these are the points E0 and consider P1. Now the center of mass of this, whenever I'm saying this disk is moving at 40 kilometers per second, suppose. So the velocity is not of every particle when I try to refer, because this, I told you, every particle would have different velocities, but whenever we refer any object is moving with a certain velocity, it is always with reference to the center of mass. So basically it's like average of this sum, and this one particle is trying to move at what speed. So the whole body velocity is generalized based on this. So take this as point C. So there are two velocities involved. One is the linear velocity, cm for center of mass, and one is for rotational. Okay, the center of mass of this is at point C. So for translational motion, okay, for translation motion, let Vcm be the velocity at point C. If you notice, this is always parallel at any instant. Vcm is parallel to the surface. Okay, this is what at the center. Now if you consider at any point P, another point will consider P2. Okay, another particle away from the center of mass. I'll draw another diagram. This is center of mass we have considered, and it is at VCM. Another suppose point there is P2, this particle. Now what is happening as per this? It is moving somewhere this side. It is trying to, okay, this is not moving straight as per this. Now look at this part of the body, it is trying to go upwards slightly. Okay, this point is trying to come up here and then go down. So as of now, at this point, it is trying to go this side. So it is not exactly parallel. Okay, so we'll consider its velocity is v2. So it will always have two components. One is the perpendicular, this side. This would be like this. This is always parallel to this, so this will always be VCM. And this will be due, this is because of the linear, and this is because of the rotation. So name this as VR, and this will be 90° always. I have not drawn it properly. This should look like 90°. So this is the horizontal component and this is the vertical component. This is the distance r2 from here. So at point P2, the velocity of particle P2 is V2. We are just assuming that the velocity of the particle be V2. Now this is not only due to the particle is not only moving forward, it is also trying to rotate. Okay, so there will be two velocities involved. First velocity is horizontal component. What is the horizontal component? VCM. So this is for linear motion because it is same, no, same direction. So this is moving forward. Okay, so it is same as this. Parallel ones will have the same thing. That's for linear. And the second velocity is the vertical component. That is VR. That is for rotational motion. Okay, this is at point P2. So what is this rotational velocity? In terms of this, rotational velocity is always r into omega. We know that what is the velocity relation? Always this normal linear velocity will always equals to r times your omega. So your rotational velocity is nothing but at r times this may be r2. If you use the letter r2, you can write it as r2. Okay, so at this point there are two velocities. Now we'll see what is happening at this point. We are done with at point 2. Next we'll see what is happening at point 1, point 0. At point P0, again let us consider two velocities. P0 has two velocities, VCM and VR. One is linear, one is rotational at this point. One is going forward, the other one will be automatically moving backward. Just try to imagine this point is this, the rotational one is going this side and the linear one is trying to move in front at P0. Okay, as per the this linear, which side is the motion taking place? The ball is moving forward, the disc is moving forward, so the forward linear one will be this. But for rotation, the disc is moving backwards, so rotational velocity will be ulta. Okay, so if disc is not slipping, point P0 is at rest. So we know that VCM plus VR is 0. Total velocity at that particular point will be 0. So basically it will be Both should be equal. So this is ulta, no? This is minus. This plus minus this should be equals to 0. Why is it so? Just look at it. This is backward direction. That's why. So when you take this on the other side, VCM will be equals to VR. What is VR? VR is nothing but R into omega. I can just randomly take it as R only. This is the velocity relation for a rolling motion. VCM is R times your rotation. At point P1, what is happening? This is also moving forward. The disk is also moving forward, both points. So VCM also will be in the same direction, and VR also will be in the same direction. Why? As per the rotation also, this point is moving forward. As per the linear, ball is moving forward. Even the rotation is moving forward. Here it was coming backward, but here it is moving forward. So both will be in the same direction. Okay, so total velocity at this point will be, if you are considering it as V1, let it be V1. So V1 will be what? Both are in the same direction, means they will get added. And exactly they'll be equal, no, at this point. Rotation as well as this. Because this is the same thing. This is also VCM. They are both parallel. This also will be same as this. This is also parallel. So this is equals to this. So when you add them, it's like having VCM plus VCM only. 2 times R omega. So at V1, this will be your velocity. Okay, so these are the various points. One we took here, one we took here, and one in middle. So if it is middle, it will always have 2 components. Here it is straight away because it's with reference to the surface. Here it will be straight away parallel with the center of mass. So these are the velocities at 3 different points for a rolling disk. The final thing is kinetic energy for that, for the rolling motion. You know that rolling motion consists of what? Rolling is nothing but translational plus rotational. So definitely kinetic energy for rolling will be kinetic energy of translational plus kinetic energy of rotation. I've already given you the table analogy for kinetic energy, that is half mv square. And for rotational, it is half I omega square. Just in terms of suppose radius of gyration you want to know. In terms of radius of gyration, this V is nothing but your, with reference to suppose this disk we are referring, then it is, you can also write it as VCM square. Forward velocity we have taken as VCM, center of mass. Whether you write this or this, it's same, no issue. In terms of radius of gyration, so the relation is what? You can just put if you want here. The kinetic energy for rolling, half, half. Instead of I can use this also. If everything you want to write in terms of VCM, also you can write. Just now we are saying VCM is what? R omega. So what is omega? VCM upon R. If in case you don't want one, this is what one is linear, the other one is rotational. Okay, just in case I want everything in terms of linear only. I don't want this, then I can use this relation. This is the relation between linear and the rotational motion velocity. So just if I want, I can just substitute here. In terms of, suppose I want the linear one, normal kinetic energy. So half, I just put the value of omega as this. So everything will come in terms of VCM only. If you are using the same letter, we'll use 1 second. Otherwise, if I'm using M here, I'll use small only. The same mass, no? Same one, smaller M. So take out everything common. So what remains is 1 plus E square upon R. This is kinetic energy for roll. In case you ask to derive the kinetic energy for rolling, this is what you have to derive. Okay, with this I finish with the chapter. The problems, whichever anything related to all the chapters which have been covered, if you all are given anything for revision, anything to solve, any of this you want me to solve in the next class, you can send. Any difficulties you all have and you want me to explain the next class, please let me know.